Ken Corum here. I'd like to take you on a review of the operation of our probes that are used for Zenneck surface waves. In this photograph, you can see our largest probe. It's 200 feet tall in Milford, Texas. And I'd like to start by asking a question that I'm not going to give you an answer to yet. See if you can answer it as we go along. What's the most important part of this probe here in the picture? The first evidence of global power for us, or that global power was possible, was an experiment done in New Hampshire by using a powerful transmitter that was operated actually by lightning and using a sensitive receiver. And what you're looking at here is an oscilloscope output where we captured the large pulse there on the left is the actual lightning strike. And you can see the energy ring down as it begins to propagate around the planet and come back. And look what happens when it comes back. You can see the pulse on the right. That's the echo going all the way around the planet of a lightning stroke using a Zenneck surface wave. In this case here, what's of interest is the time difference between pulse to pulse. That distance identifies the frequency of operation for one wavelength around the planet. In our case, it's exactly what Tesla described in 1899 in his notebook. The other aspect here is called the decrement. Here you can see the amplitude of what we call A, the amplitude of the big pulse on the left, to the amplitude of the smaller pulse on the right. And you can see that it's roughly 70% the size of the original. That means for the energy to go all the way around the planet and come back, we only lost about 30% of the energy. Now with copper wire, it would be a whole lot more than 30% to get all the way around the planet and back again. Think of a copper wire going all the way around the planet once. And this was our first indication that yes, indeed, Tesla did do the experiment in 1899, and as it was our first indication that yes, we can improve or engineer global wireless power. Here's an example of a Zenneck surface wave versus radiation. The radiation is the dash curve, and the upper curve that's got a knee in the curve in the middle of the graph there, that is a Zenneck curve. And you can see the circles which indicate the measured data. Here we're operating at the 160 meter handband, roughly 1850 megahertz, with a small probe. And here we actually got a very good fit to a Zenneck surface wave, what's predicted for a Zenneck surface wave. So here the measured data is fitting the predicted curve. Here's another device. You can see the photograph on the left. There's a metal plate with a ball above it and a phasing coil between them. And this apparatus, we call it a polyphase system because it's got two probes, not one. And it produced the curve on the right. And here again, you can see the red line indicates what the Zenneck solution predicts. And the red circles indicate the measured data from this apparatus. So again, we have a lot of confidence that our probes can now produce a Zenneck surface wave. Here's a closer view of the same thing. Here you can see a radiation device. That's a half-wave dipole. In this case, we're in the 50 megahertz range. And on the right side, you can see a small probe there. You can see a ball with a metal plate, and in between it is a phasing coil. Because remember, we have to match the fields on the Earth in magnitude and phase. Here's our experiment, a reproduction of an experiment from 1936, which was done under the auspices of Bell Labs by Charles Burroughs on that same spot. And they concluded that surface waves do not exist because their apparatus and their data only showed radiation, which is the magenta curve. Well, if you use a device designed for radiation, which is what's in my left hand, you get that magenta curve. You get radiation, and that's it. However, if you use our probe, which is in my right hand, the data then fits the predicted Zenneck curve for a Zenneck surface wave. Here it is up close. You can see two charge terminals. We have two spheres, in this case here, two doorknobs that we're using, and they act as charge terminals to produce electric fields on the ground, and a phasing coil over on the right where we can adjust the phase between the two. So now we can match the fields that Zenneck is predicting on the surface of the Earth, both in magnitude and phase. We did do a presentation under the auspices of UNESCO for Serbia. And the reason we were in Serbia is that's the home area for Nikola Tesla. And this was July 2015. UNESCO had once a year, they have a group of engineers from all over the world that come together and look at new and upcoming technologies. And we were pleased to do a presentation on our work of Zenneck wireless power. Here's another graph from December 3rd, 2014, where we're measuring field strength versus distance. Again, you can see the magenta line, which is where radiation would be. So you can see for radiation, the field strength isn't very strong compared to that of a Zenneck surface wave, which is the line above, the red line. And you can see our data is matching once again to a Zenneck surface wave, not a Norton ground wave. Here's another graph. We're at 400 kilohertz now, so we dropped from 50 megahertz down to the 160 meter handband, which was 1800 kilohertz. Now we're down to 400 kilohertz. The predicted curve is the red line. That's a predicted curve for a Zenneck surface wave at this frequency. And you can see the blue line, or the blue dots, which indicate what we actually measured. So once again, we have a lot of confidence in our device, our Zenneck surface wave probe, to produce a Zenneck surface wave. We continued our research, and now we went from 400 kilohertz to 200 kilohertz. Now we're dropping down in frequency. Remember, everything is always measured in terms of wavelengths. The wavelength at 200 kilohertz is extremely long. In this case here, we have a probe, and you can see there in the picture, it's much taller than the ones we were using at 50 megahertz, which was the two doorknobs separated by about 6 inches. Now the probe is on the order of 70 feet tall. And here, once again, you can see that the measured data is fitting the predicted data for a Zenneck surface wave, and our Zenneck surface wave is now exceeding 200 miles in distance. Here's another curve. We went from 200 kilohertz now down to 100 kilohertz. So we're dropping down in frequency. The wavelength is getting longer, so we're going to push out further in distance over the surface of the Earth. And you can see our probe now, which is up there at 70 feet above the ground. And you can see the probe got a little bit bigger. From the picture, you can't tell, but those spheres, there's 4 charge terminals there connected together, are 2 feet in diameter, 12 feet apart. So you can see that's fairly high up there for this frequency. However, at this frequency, a wavelength is very long, so it's very short structure in terms of wavelengths. There is something very unique about this measured data, though. The red curve is what Zenneck predicts for the surface of the Earth in this part of Texas. Our data fit all the way out to 100 miles. We're matching Zenneck's predicted data beautifully. But something happened at 100 miles to make the data go off the curve. What's 100 miles south of Dallas? What happens in the Earth 100 miles south of Dallas? Well, you begin to hit something unique in the ground, which means the ground is changing, which means the propagation mechanism, which is predicted by Zenneck, is going to change, because the propagation mechanism is dependent upon how conductive the Earth is. So why does the conductivity change 100 miles south of Dallas? Well, I can tell you, 100 miles south of Dallas is the beginning of the oil and gas fields as you go south on Route 45 out of Dallas. So here what we're doing is we're predicting a Zenneck surface wave out to 100 miles, and it jumps over to another Zenneck surface wave from 100 miles on out to 300 miles. And you can see that here in the curve, the measured data. So we're beginning to use Zenneck surface waves now to detect abnormalities in the surface of the Earth or what's in the ground. Now it depends upon frequency. So at 100 kilohertz, yes, we can identify the gas and oil south of Dallas. However, 100 kilohertz you wouldn't be using for global power. You'd like to get down, as Tesla says, below 10 kilohertz. We'd like to get down to 400 hertz. At that point, essentially, the mountains of the Himalayas are flat. There is no peaks and valleys and changes in conductivity as you go around the planet. It becomes a uniform sphere of a certain type of sigma, a certain type of conductivity. Here's a smaller operation, which again is done in Texas. We have two plates now. You can see the plate above, plate below, and we're operating here at frequencies roughly in the 40 meter hand band and the 80 meter hand band as well, and also in the 160 meter hand band. You can see the two plates which act as charge terminals. You can see the red device standing vertically there on the table. That is a phasing coil. Remember, we need to match not only in magnitude but also in phase of the electric fields that impinge upon the surface of the Earth. And again, you can see the red curve which is predicted, and the data fits the curve wonderfully. As we continued on, we also investigated other avenues where we could use 100 kilohertz. Well, at 100 kilohertz, that happens to be the frequency for low-RAN navigation, which was slowly being phased out. And we came up with a proposal to use our equipment now for communications, or essentially navigation, rather than power distribution. So instead of having 400-foot towers scattered all over the coast for navigation over the oceans, and each one of those towers being powered by 10, 20, 30 kilowatts worth of power, we can come in with a 70-foot probe, which will do the same thing and only be operating maybe 500 watts to 1,000 watts. So a considerable savings in energy to accomplish the same thing. So now we can get navigation using this device. And you can see a commercially created coil here in the picture. This is a phasing coil for 100 kilohertz. This is not a Tesla coil. We didn't create a Tesla coil here to make super high voltages. This is a phasing coil. When you go back and you look at the coils in Tesla's Colorado Springs notebook from 1899, don't think big sparks. Think a change in phase. It is a phasing coil used to change the phase of the electric field produced by the probes, which then the electric fields are impinged upon the Earth with the correct phase. Now, what about power? Well, for global power, a while ago I mentioned we need to get below 10 kilohertz. Why? Because Tesla said so. Well, that's not good enough. Why 10 kilohertz? Well, I mentioned this earlier. We need to get down to where we're dealing with one or two or three or a handful of wavelengths to cover the entire planet. Remember, the energy in a Zenneck surface wave only propagates in terms of a certain number of wavelengths. Well, if we can get down to where it's one wavelength around the planet, or at least 5 wavelengths around the planet, we can now begin to transfer significant amounts of power. So we go back to our tower, which was on the original slide. A 200-foot tower with charge terminals inside the tower and on top of the tower, and phasing coils in the tower, and half a megawatt generators beneath the ground below the tower. We begin to turn this stuff on. And as we do that, the Zenneck surface wave that's predicted is actually that black line, that black curve. And notice we go out in terms of miles. 1 mile, 10 miles, 100 miles, 1,000 miles, 10,000 miles. How far is it to the opposite side of the planet? We're here in Dallas, Texas. Where is the opposite side of the planet? Somewhere in the Indian Ocean. Well, if we want to transfer power to the Indian Ocean, we need a frequency where the knee in the curve is at least that far. So we have to lower the frequency. In this case here, we're operating in the region of 20 kilohertz. Actually, we were down at 18 kilohertz for this graph. And you can see the data matches the curve. Now, we were not running megawatts in this. This was the very first time we powered up that tower. And we were operating about 1,000 watts, roughly 1 kilowatt of power going in. And we were able to match the data, the measured data matches the predicted Zenneck surface wave, which means if we ran that 1 kilowatt power up to a megawatt, you're going to have significant amounts of power available to you, in this case here, out there 2, 3, 4,000 miles out. So think of a big circle, 4,000 miles centered around Dallas. Anybody in that circle now can pick up that energy and use it. As we go lower in frequency, that circle gets bigger. So once again, we're not creating energy. We're not supplying free energy. We are supplying a mechanism which will transfer the energy from one place to another. In this case here, from the Dallas area to a circle that's roughly 4,000 miles in diameter. Here we are inside the tower. And inside the tower, you can see very large cable going up inside the tower here. The spacing of the cable, the number of turns, the diameter of the cable, all these things are factors which have to be considered in designing this mechanism for a given frequency. So as you go lower in frequency, this phasing coil has to change. And it's not an easy thing to do to just simply go in and change the tower's frequency. For these low frequencies that go global. So this was our first attempt in commercializing global wireless power. Here we are in our simplest form. If you really want to know how all this looks like, the simplest form is just simply 2 charge terminals with the appropriate amplitudes and the appropriate phase difference between them to create electric fields which add up to a given electric field impinging upon the Earth with the correct magnitude and phase of what Zenneck predicts for the material that makes up that surface, in this case, the good Texas soil. Below the Earth, we have images which we also have to take into consideration. And those images affect how the electric field is going to look like. So we have to combine all of these together to get a Zenneck surface wave match. And once you do, you will follow that predicted Zenneck surface wave curve. Here we are in 1899. Everything we're doing today was done over 100 years ago in Colorado Springs. Notice the similarity between this and the previous slide. Notice the 2 charge terminals. Notice the building. And if you look at Colorado Springs notebook that Tesla assembled for us, you will see coils, big coils, little coils, fat coils, thin coils, tall coils. These are all phasing coils so he can get the correct phase relationship between these 2 charge terminals. Now, the mathematics did not exist when Tesla did this work. The equipment that we use today didn't exist when Tesla did his work. Tesla had to use intuition, imagination, and a lot of previous experiment by trial and error. It was not an easy thing for Tesla to do this. Tesla actually invented an oscilloscope using a flashing light to determine frequencies. Today, we just go pull an oscilloscope off the shelf and we can get the time domain of a sine wave and see exactly what's going on. Tesla didn't have that luxury. Tesla had to make his own equipment. Well, people today say, all right, the Corum's just copied Tesla's patents and that's it. No. The Corum patents are not copies of Tesla's work. It's a continuation of Tesla's work. What Tesla did in 1899 and on up through 1900 to 1906, before he ran out of funding in Long Island, is absolutely Tesla's. It belongs to no one else. He is the inventor. What we do is we pick up his thread and bring it up to the 21st century. The Corum patents unravel a 100-plus-year-old mystery, and that mystery now has been brought down to engineering levels where we can now engineer global wireless power for the very first time. How do the receivers work? What are they going to look like? In this case here, you can see on the left side, we have our transmitter. Here's our phasing coil and our charge terminals that produce the Zenneck surface wave on the air-earth boundary. And over on the right, we have a receiver. Notice the receiver looks like a half-wave dipole. Well, it's not quite. What we want to do is we want to pick up the electric field that's propagating along that boundary. So we can use any vertical probe or any probe that matches the fields, and then with a matching network, match the impedance of that probe into the load, in this case a light bulb. And what you will see is power transfer. You will see power go into the light and power come out of the transmitter. This is a very important thing here because radiation does not do that. We are operating a constant voltage system. A Zenneck surface wave gives us the ability to make a constant voltage system. Just like the electric outlets in your home. Your electric outlets may be 120 volts. When you plug in a toaster, it's still 120 volts. Radiation cannot do that. Radiation is referred to as a constant power system, not constant voltage. A Zenneck surface wave gives us the ability to have that mechanism. Another way to think of it is think of solar panels. If you put a string of solar panels in your backyard or on your roof, are you dimming the sun because you're taking energy out of the sun? I don't think so. In this case here, we actually have a physical connection through that Zenneck surface wave. It's a waveguide propagation mode. Energy goes in, energy comes out. If you take energy out, you will see a drop in the energy going in. That's referred to as a constant voltage system, and that's exactly how our power system works today. Again, we can see here what's going to happen. On the left, we have a transmitting probe. On the right, we have our receiver, just like in the previous pictures. In this case here, we're operating 10 watts, and we have a 10-watt light bulb lit up. We're stuck, though, in terms of frequency. Remember, the propagation mechanism is always in terms of wavelength. So if we have a short wavelength, like 50 megahertz, we're not going to propagate very far. So you can see here, 10 wavelengths out, we're getting 10 watts. If you want to propagate further, you've got to go lower in frequency. If you want global propagation, you've got to get considerably lower, where you're in terms of wavelengths to get around the planet. Here is a movie showing precisely reception of the power here, the 10 watts that we saw in the previous slide. And it actually, we can see the brilliance of the light bulb show us the shape of the Zenneck curve. So as I start about 20 feet away from the Zenneck probe, you can see the light is very bright at step 1. I go to step 2, it gets a little dimmer. Step 3, a little dimmer. Step 4, a little dimmer. And step 5, it begins to go out. And at that point, we're all the way out there, like 300 feet. So as I walk from 20 feet out to 300 feet, you will see the shape of a Zenneck surface wave.
Okay. All right. Go ahead. Okay, now we're on your, how far are you? About 15 feet, 20 feet maybe?
About 20, 25 feet.
Okay, let's go ahead and move back. I think you're on the ground there, down there. I'm going to get over this side to give perspective on how far we are away from the probe at this point. So yeah, it's over there a ways. Keep going.
Yeah, so we're at about 10 wavelengths.
See, this way you can actually talk about how far you are out when you just, you know. At some point it's supposed to die on us, isn't it? There it goes. Yep.
As I mentioned, frequency plays an important role. So in this case here, you can see at 10 megahertz, the energy, or I should say the distance that a Zenneck surface wave is capable of carrying power is very short. So at 10 megahertz, you got a lot of power in it, but it doesn't go very far. At 1 megahertz, it goes a little bit further. At 160 kilohertz, it goes a little bit further. At 10 kilohertz, you can see it's a flat line. We can't fit on the graph where the knee and the curve would be way out there. So essentially, we're propagated around the planet at that point. But notice the initial levels are lower. All right, it's all in terms of charge. How much charge can I put on those charge terminals? And that's going to determine how much energy I can draw out of the system. So all of these graphs here indicate the same amount of charge on the terminal. So you can see roughly the area under the graph is the same on each one. So the question then becomes, well, how do I get more charge? This is where you go after the big sparks. You want to design the system to raise the voltage high enough to get the charge on those terminals up. And as the charge level begins to rise, you're going to get even greater distance of propagation or more energy available to the users. This is another important slide, and that is in terms of what's the propagation loss to the antipode. Antipode is the opposite side of the planet, or should I say antipode for the English-speaking world. Here you can see at 100 kilohertz, you see the frequency on the horizontal axis. We go to 100 kilohertz, we go up the curve and across, and you can see the dB loss. It's like 58 dB loss for a 100 kilohertz signal to go all the way around the planet and come back. That's not practical. I mean, even for communications purposes, that's not practical. But if we drop down to 10 kilohertz, look what happens. At 10 kilohertz, we have about 1 dB loss to cover the entire planet and back again. 1 dB of loss, that's nothing. That's far better than copper at this frequency. So if you had copper wire wrapped around the planet, we've got something which is much more efficient than copper wire. So in this case here, you can see a Zenneck surface wave depends upon what we want to do. Do we want to do communications? Do we want to do short haul, long haul? Do we want global power, global communications? All these things have to be considered and designed according to these graphs, which we've determined, just as Tesla said. This we refer to as the Corum-Zenneck theorem. Basically what it is what we need to do to make all this work. On the right-hand side, you see an equation, right, which is called the passive load. That's the air-earth boundary. That's what a Zenneck wave would look like in mathematics. On the left, we want to create a device that matches the magnitude and phase of that equation. So you can see we have to deal with the magnitude of two electric field vectors here. One is the vertical electric field, one is the horizontal electric field. And we have to match the phase between them. When all those conditions are met by the source, a wave will now propagate according to the predictions of Zenneck. Well, are there other places in this universe a Zenneck surface wave is useful? Anywhere you have a boundary between two lossy mediums. Think of the moon. The moon has a solid surface, lunar dust, lunar rock, and a vacuum. Those two are lossy mediums. So we can actually have Zenneck surface propagation, surface wave propagation on the moon, on Mars, on any place where we have a boundary between two slightly or non-conducting interfaces. In this case here, we could actually have wireless power on the moon or wireless communications around the moon without satellites. Here's an example of propagation on the moon. Just for fun, we took what NASA gave us as the conductivity of the soil on the moon. And from that, we know what the properties of vacuum is. That's the air around the moon. In this case here, it predicts that red and black line that goes across the top. That's where a Zenneck surface wave would be in terms of amplitude and distance. Look at where radiation would be. That's the magenta dashed line on the bottom. So on the moon, we would have a tremendous amount of capability of transferring power, or very simple communications with low power for communications around the entire moon. Our current facilities, where we are now, you can see we have office space, we have classroom space where we do training, and we have a laboratory and facility where we can construct almost anything that we need. Even today, in the 21st century, we're finding that we still have to build a lot of our own equipment. Because at these frequencies, when you get down below 10 kilohertz, there's nobody down there except for submarine communications doing radiation. They don't do Zenneck surface waves. So the equipment that's required, the electronic equipment, we have to build our own in many cases. Here's our tower. You can see it's roughly 200 feet tall. A large charge terminal up on top, the phasing coil in the building. It's all air controlled inside and underground. We have a facility with a 1 megawatt capable generator. It's currently only configured for half a megawatt right now. And a matching network to go with the 1 megawatt generator to get the energy out of that generator into the phasing coil. And we have a remote control room on the other side of the property, because when this is in operation, you don't want people next to the coil. And that brings up a whole aspect of questions. Is it safe? Can people steal the energy? What about this? What about that? And we'll get into that much later. Here's some more equipment. Here's a 50 kilowatt generator on the left. Here's our small probe in the middle. This is used for AM broadcasting. However, not only does it work for communications, for AM broadcasting, for AM radio, it also can be used for demonstrating wireless power over short distances. And you can see the receiving mechanism there on the right. And we have a 1 horsepower motor there. We have a 1 horsepower motor generator pair. So we can use a generator to convert frequencies. Basically, we have RF frequencies coming in. We convert it to DC to drive a DC motor, 1 horsepower motor, which converts it to 60 hertz, and so on. Basically, whatever you need to do, you can do on the receiving side over the short haul demonstration. To date, this is what we've got. We've successfully demonstrated the science. We've delivered over 50 technical manuals describing the physics in great detail. We've authored hundreds of patents. Matter of fact, I believe you add up all the patents together, there's over 1,000. We've successfully constructed devices that work at 50, 1800 kilohertz, 1300 kilohertz, 200 kilohertz, 150 kilohertz, and 19 kilohertz, which was our global test. Unfinished to date, we'd like to do 1330 for AM broadcasting, a full-blown commercial station. For 100 kilohertz, we're still trying to complete the E-LORAN mechanism for navigation. And at 17.9, we'd like to raise the power level to our full half a megawatt capability. These are the things that we have planned for the future.